let's start. Do you have any questions? All right. So I'm going to switch to my iPad. So once again, I won't be able to see your chat. If there's any interaction, please speak into the microphone. All right. So last time we were talking about chapter 1, basic, right, combinatorics. Okay. And the reason, right, we do this is because we want to be able to count, right, the number of possibility, right, the number of possibilities in certain kind of experiment. All right. And basically, I mean, I'm trying to explain the connection between, let's say, combinatorics and discrete probability, okay? So, which is, of course, right, what this course is about. It's not about combinatorics, but we're gonna be using combinatorics as a tool, right? When we do probabilities, when we do discrete probability. Well, you know, most notably, right? Because, for example, when we have an experiment, we make the assumption that all the outcomes are equally likely, right? So again, I mean, one of the example we can think of is like, let's say we toss a dice twice, right? And so in this case, right, if all outcomes are equally likely, and right, using the multiplication principle, there are 6 square, right, possibilities total. And that's exactly right. For example, I mean, this is just a very small application of combinatorics, but right, there's 6 square possibilities total. Then, right, the probability of any of this outcome, right? For example, the probability of getting, let's say, a 5 and a 1, right, is going to be 1/36, for example, right? Because when all outcomes are equal likely and we have 36 outcomes, right? Things like that. Anyway, right? So when we deal with basic combinatorics, we should pay attention to the basic principles, right? Which are, the first one is the multiplication. All right, which says something like this. Suppose we have so many groups, right? Let's say group 1, group 2, group 3, right? So on and so forth. And we choose, right, one option, right? One object from one choice from each group. And the key word here is and, right? Okay. So we choose one choice from first group and one choice from second group and. Then the total number of possibilities, right? Sorry, this is n sub r, right? The total number of possibilities n1 times n2, etc., right? Times n sub r. Okay, like that. And now, I want to say this because you know, the following is not really something that the book mentioned, but you can say here's one prime, right? The principle is addition. It's not really a principle, but suppose that you make one choice from group one or group two or group three or group R, right? The keyword is or. Then the total number is N1 plus N2, etc. plus NR. Is that okay? So we want to pay attention, right, again, to the description of whatever that is going on so that we can solve the problem correctly. So as an example, right, let's take a look at, so this is the first quiz, number 18, right, which is one of the problem assigned on your homework, right, which says the following. A student has to sell 2 books from a collection of 6 math, 7 science, and 4 economics. Okay. How many choices are possible if, right, A, both books are to be on the same subject? Okay. So again, let's take 1 minute. See what answer you come up with, and then we'll gonna discuss. Okay, so what's the answer here?
6 times 5 plus 7 times 6 plus 4 times 3.
Yeah, but I would prefer, that's great. I would prefer 6 choose 2 plus 7 choose 2 plus 4 choose 2, which is what you say, but right. So the reason, right, that I prefer this over the other answer, and by the way, right, and your answer is okay. There's actually even like a, let's say, a worse answer. Let's say the answer is what was it? 6 times 5 is 30, right? 7 times 6 is 42. 4 times 3 is 12, right? So if I'm not mistaken, the total answer here is 84, right? Well, whatever. The worst answer, if 84 is the thing, is an 84. This is worse. Worse in a sense, right? That first of all, this shows no work or no idea. Okay. And by the way, I mean, if you look at the back of the textbook, the answer provided will be something like that. Let me check real quick just to make sure that it is 84. Doesn't matter, but hold on. It'd be 42, right? Oh, yeah, exactly. So what you said actually, right, is has to be divided by 2 because it's choose 2 exactly. So yeah, right. So there you go. So this is 42 actually. Yeah, okay. So yeah, it's not 6 times 5. 6 times 5 would not account for would take order into account, but here order doesn't matter as implied in this question. Anyway, right? So 84 is wrong. 42, even though it's right, is also not the right answer in the sense that it's no work. And let me explain real quick here, right? Again, right along those lines, when you write something like this down, you sort of explain the reasoning behind your work. Or if you want, the best way is to write down another line in English, okay, for the reason of your expression. For example, right, the reason here is right out of 6 math books, we choose 2, right? Or out of 7 science, we choose 2, etc. Okay. And I'm saying this, right, again, I guess in connection to exam and things like that. I don't care for the final answer in the sense of a number, a numerical answer, because numerical answer means nothing. All right, even if it's correct, because you could have just called your friend and asked what's the answer, and they tell you 42, so you write down 42. And of course, right, if you write down something like this and it's not 42, you get no credit. If you write down 42 and there's no work, you probably get very little credit. If you write out something like this, okay, and if it's correct, that's good. But if you write down something like this is slightly wrong and you write down the reason, you might get partial credit, or you might get a lot of partial credit. If I see that you're in the right track, you just kind of missed something, like you did not realize that order matters or order doesn't matter, blah, 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 in this kind of question. Okay, now we're clear on this. Any question? All right, so the second question will be the books. So the same question, right? So the students has to sell 2 books, blah, blah. How many choices are possible if the books are to be on different subjects?
So question B is 6 times 7 plus 6 times 4 plus 7 times 4.
6 times 4, that's correct. That's correct. Good. That's the right answer. And again, right, if you want to be careful and you want to make sure, right, you cover all ground, you can say reason, right? What? So you can say, for example, what there's 6 math, right, and then 7 econ, and you pick one from each, right?
Would it also be correct to say like 6 choose 1 times 7 choose 1 plus and then so on?
Yeah, yeah. That's also acceptable. Yeah, which is right. By the way, the multiplication principle, right? As we say, as now you notice, right? Exactly, it's n1 choose 1, n2 choose 1, etc. Right? Yeah. So this is fine. It's probably a little bit an overkill, but that's fine, right? Pick one from each. Using, right, let's say multiplication principle. And so on. And the and so on here is acceptable, because what you're trying to say is you explain this way of, you know, counting, and the other ones are similar, right? So that's really it. But yeah, that's the answer. All right, any question? And so, right, this question right here demonstrates, right, exactly the principle both on addition and on multiplication, right? You see, because you multiply 6 times 7 because it's, let's say, math and econ, right? And then you add because you say or math, or, you know, yeah. So here, right, you can say math and econ, or math and science, or math and, sorry, econ and science, right? Right. Yeah, and I guess this right here probably would be the complete reason for counting. Okay, but I'm just saying, right, the reason here is sort of like a insurance policy, but you should do it, especially when the counting problem becomes a little more complex, right? To explain your idea, rather than just, I mean, of course, if people know counting, they should see what you're doing, but don't count on it, right? Writing down some English statement would be very helpful. All right, are we good? Now, so the next principle, right, is so those are the basic ones. The second, right, is permutation. Whoops. So the first one is the permutation of an object, right? Let's say distinct, right? And here, you see, with each of the principle, you should have an example in mind of what you're trying to count, right? So, for example, 1, 2, etc., up to n, then you have n, 2, 1, etc., up to, right? So you swap things around. You know what? It's probably not good to have too many, right? 1, 2, 3, 3, 2, 1, 2, 1, 3, etc., right? These are permutations, right? So the answer, of course, is n factorial, right? Because you have n choices for the first position, right? And then based on the first choice, you have n minus 1 choices for second position, and so on and so forth, right? And then you use multiplication principle to multiply together because it's first position and second and third position, etc., right? Now that's 2A. 2B is permutation of, right, let's say n1 plus n2 plus nr objects, right? Objects within each group are identical, right? So what we mean by this is, right, there really are groups, n1 in the first group, n2 in the second group, etc., right? And within each, we cannot distinguish. So what's an example, right? For example, you can have 1, 1, 1, 2, 2, 3, 3, 3, 3, right? So here, the number of groups, right, R is equal to 3, right? And 1 is 3, and 2 is 2, and 3 is 4, right? There are 9 objects total. But for example, right, here's one permutation. Right, this is one possible permutation. But we clearly see, right, so this is of course different from this. But if we permute, right, the threes among each other, right, if we fix everything else, we just permute the three among each other. Meaning, right, suppose you write 3 sub 1, 3 sub A, 3 sub B, 3 sub C, 3 sub D, right? I mean, we do this so we pretend we can distinguish as 3, and you write like this, right? Then these actually are the same thing because, right, objects within each group are identical. So we're doing this to demonstrate, right, that there are 4 factorial ways to permute things within each group. I mean, within the group of number 3s that we don't care for. So in other words, right, this is trying to explain that then this number of ways is going to be the sum, right? This is n equals n, right? I guess the textbook would write like this: n factorial over n1 factorial, n2 factorial, etc., and r factorial, like this, right? As a product. And as I explained, right, the reason is basically you have n factorial total number of ways to permute everything. But then, right, within each group, there's n sub r factorial ways to permute among themselves. Within each group, that doesn't count, right? Anyway, this, as we also note, is the notation for the multinomial coefficient, which is, right, the number of ways to choose objects, right, into each group. Anyway, if you think about it, there's slightly different concepts. They describe slightly different things, but they end up being the same number. And the reason is they can be, right, viewed, they can be cast, right, from one point of view to another. So we should recognize both, and eventually, right, we're just going to adopt this notation. So it's a multinomial, right, coefficient, okay? But right now, we're going to just use it under the banner of permutation of so many objects. Objects within each group are identical. All right, so what's an example? The example is, oh, okay, so actually this is quiz 2, right? So this is question number 32, right, which is also from your homework. It says 10, let's say weightlifters, whatever, but let's just say athletes, right? Compete, right? 3 from the US, 4 from Russia, 2 from China, and 1 from Canada, right? They say that the scoring takes account of countries, but not individual identities. Question A, how many different outcomes are possible from the point of view of scores? Okay, so that's a question. So once again, I guess I'm introducing this question right after I tell you the principle, so you probably can guess, right, what to use without thinking too much about it, which is okay, because this is a lecture. But what you should do is actually you should really try to think of what the question is really asking, because as I say, the language of combinatorics can be a little bit vague, and until you can be completely clear on what are we counting, right? Usually that's a question. Then I would say that most likely you're going to come up with the wrong answer. Okay. So in other words, I mean, I myself, right, when I read this question, I kind of feel it's kind of weird. What do we mean by from the point of view of scores, etc.? Okay. But of course, right, the keyword probably is from here, right? Scoring takes account of countries, but not individual identities, which of course, right, is really a hint to say that the athletes, right, within each country are not distinguishable, right, are not distinct. So maybe, right, the best way is to give an example to illustrate for ourselves what's going on. For example, right, we can say, suppose we have US, right, and then US, and then China, and then Russia, right, and then Canada, Russia, right, China, US, whatever, right, like that. That's one ranking, right? And then we can imagine, right, that so these are, of course, right, different individuals from US, right? And it could have been that this athlete right here, athlete number 2, outperforms, right, athlete number 1. In other words, the outcome is reverse within, right, these two athletes. But we see that from the country's point of view, I guess, I don't know what they mean by view of scores, it's still the same ranking, right? Because it's the 2 US on top, and then followed by China, etc. Right? I mean, if you follow Olympics, you probably see that, right? Most of the time, people don't really know who the athletes are. They just say that, well, China or US, right, won the top 2 spots, and then followed by blah blah blah. Okay, so that's what that really means. But I'm explaining this, and probably some of you will feel that it's already obvious, but some of you might feel it's not obvious. Who knows? I mean, in terms of the question, and I encourage that you feel the question is not obvious, then come up with your own example until you're completely sure that this is exactly what the question is asking, right? Then we do the answer, right? Well, having explained that, right, then what is the answer here? It should be 10, choose 3, 4, 2, and 1. That's it, right? If you want to write down a reason, we can say this is the permutation, right? Of 10 objects, right? In which groups of 3, 4, 2, 1, right? Objects are identical within each group. Okay. Any question? Okay. So question B says how many different outcomes correspond to US having 1 in top 3 and 2 in bottom 3.
Is it
What's the answer? Yeah,
Is
go
it-
ahead.
3 choose 1 times 3 choose 2 times 7 factorial over 4 factorial times 2 factorial?
Yeah, I believe the last one you referred to is the multinomial coefficient, right? 7, 4,
Yeah.
2, 1. Correct. Good. Yeah, there you go. Very good. And I'm gonna be a bit lazy here and not write down the reason. Can you tell me the reason? What's the reason for this expression?
I thought of it as like in the top 3, you have to choose one US athlete, and then the bottom 3, you're choosing 2, and then you have 7 left over, but 4 are the same, 2 are the same, and 1 is the same.
Excellent. That's exactly is the reason. And if you write that down, then that's completely perfect for that answer. Good. All right. Any question about this? All right. So that's permutation for you, right? But notice that, well, we're kind of using the combination number anyway, right? So, which is the next principle, right? Now, principle number 3 is combination, right? And combination is at the heart of it. I guess the easiest one is the number of ways. So A, right? Number of ways to pick or to choose, right? R objects out of, right? N objects, right? In which order doesn't matter. And this word has always been and will always be, right? Sort of like a something where people would debate about, like last time when some students asked this question before, right? The best thing I would say here is, sure, you should pay attention to this, but don't make a big fuss about it, right? Basically, what it means is like you have a bag of N objects. You reach in and you pick out R at the same time, and you just note what objects they are without caring for the order in which they come out. So you don't pick them out one by one, so to speak. Now, anyway, right, here the answer is N choose R, right, as we all know. And if you write down the expression, which is not required, by the way, unless I asked you to write down the math, N factorial, R factorial, N minus R factorial. So what I'm trying to say is you should always know what N choose R means. But for this class, unless it's required, this suffices, right, for the answer. I would assume that you know this. So again, just trying to demonstrate, for example, in this question, right, we should see that the question, the implication is that the order doesn't matter, right? Out of 6 books, the student choose 2 books to sell. Is 99.9% sure that the order that the student sells the book in is not what the question is asking. Well, is that okay? Things like that. So that's combination. And it is also called the binomial coefficient, right? The reason is because we can have something like this: x plus y raised to the nth power will be the sum, k runs from 0 to n of n choose k, x to k, y to the n minus k. All right. So the reason, of course, is you expand this into, right, n factors, and you choose k factors to be the x, the n minus k factors to be the y, right? This is the binomial formula, right? Binomial expansion. And you should know this, right, expansion, and you should know the reason why it works this way. One thing to note, of course, is that, right, the binomial coefficient is symmetric. In other words, right, you could have this working for you. It's a bit weird. People won't write like this, but it can be like this, right? So in other words, if you instead of running, let's say x from 0 to n, you can run x power from n to 0, right? And it will be exactly the same because it's symmetric across, right? So it doesn't matter. So and also we are saying that n choose k is equal to n choose n minus k. What's the reason? The reason also can come from interpretation. When you choose R objects to be inside, then you also choose n minus R objects, right, to be left out, right? Like that. So that's the binomial coefficient. B is a generalization of this, right? The multinomial coefficient, which you should realize is a generalization, okay, of the binomial coefficient. So this is exactly the number of ways to choose, right, n1, n2, etc., right, and R objects, right, into R groups, right, out of n1 plus n2 plus nr, which is n objects, right? And so the binomial coefficient is when r equals to 2, right? Now, the answer, of course, is the multinomial coefficient, but one way to see this is, right, for example, is you, first of all, you pick out of n objects, you pick n1 to be in the first group, and then the remaining n minus n1, you choose n2, okay, to put in the second group, so on and so forth, right? And then, of course, you have, right, the final object, which is like that. But really, right, when the remaining, this is really just NR anyway, because when you take away all the other groups, you have NR objects left, you choose NR, so there's only one way, right, to put into the last group. But if you look at this expression, what is it? It's n factorial over, right, n1 factorial, n minus n1 factorial, right? And then you have n minus n1 factorial over n2 factorial, n minus n1 minus n2 factorial. The key, right, is that you see this and that simplifies, right? And then, of course, you look at the next expression, you have the simplification going on right here, so on and so forth, right? So when all the cancellation happens, you end up with exactly that, permutation thing that we looked at, which is also called n choose n1, n2, and r, right? Okay. And the multinomial coefficient, there's also a, right, multinomial expansion, but for obvious reason, it's not very easy to write down with a lot of terms. Let's just write down with, like, say 3 terms, right? Let's say x plus y plus z to the n. What would that be? It will be the sum, right, of x to the, let's say, I, y to the j, and then z to the n minus I minus j. The coefficient in front of it is n choose I, j, n minus I minus j. Like that, right? Where ij runs from 0 to n. Okay. Any question about this? All right. So want to do the rest of the problems, we'll go over the rest of the problems from the homework. Not necessarily illustrating any principle in particular, except one, right? That I'll and it's not one of these principles anyway. But again, right, the point of the remaining questions is to show that you have to combine this principle in a correct way, right? To come up with the answer. There's no unique formula for all the questions. So next question is number 22, I think. Right? It says a person has 8 friends. Of whom 5 will be invited to a party. So A, how many choices possible if 2 friends are feuding, arguing, and won't come together? Okay, so again, this is like kind of like a, I don't want to say typical, but kind of typical, right? Combinatorics question. Obviously, you do some sort of 8 choose 5 thing, but with a twist, right? Where out of those objects, you are careful not somehow to have 2 of the objects to show up together. That's kind of right the taste here. All right, what's the answer here?
Is it something like 6 choose 5 plus 7 choose 4 times 2?
Not so sure, but let's write down. Say 6 choose 5 plus 7 choose 4 times 2. Can you explain your reasoning?
My reasoning is that 6 choose 5 comes from if both friends don't come, or well, both of these people who are feuding don't come.
So
and then
both friends not invited, right? Okay,
yeah,
that makes sense.
and then 7 choose 4 would be if one of them attends, or one of them is invited, but not the other. And
Right,
then
so
times
that's where
2 would be just
that's
replacing one with the other.
well, I guess, or here the 2 here is choose one of the friends, right?
Yeah.
To invite, right? And then you have 4 left because you need 5 total, right? And choose the
Mhm.
remaining 4 from the 7. Oh, and by the way, right, do you see a mistake here? Choose one of the friends to invite. And then you choose the remaining 4 from the
Oh, 6. Yeah.
Agree? Yeah, so
Yeah.
you see the advantage of explanation, right? Because exactly when you write down this reasoning, you will see where your logic goes wrong or not. Choose the remaining 4 from the 6, right? And again, right, I'm doing exactly what I tell you to do, just in a lazy way, meaning that I'm not writing down in English, but this is fine, right? But you see that exactly when you do this, you cover all ground. And even if you make a mistake somewhere, I can follow your reasoning and give you partial credit if you make a mistake. Any question? All right.
Could you also like get the total number of combinations and then subtract from that to get the answer?
Yep, that's called negative counting. That's actually a good way. Yes, in which actually a problem we will do this way, but can you, that's valid, by the way, but how
Yeah.
would you do that? So
So
can you
I
tell me what your
thought you'd
answer
get
will
the yeah, I thought you'd get the total number with h is 5,
Okay.
and then you could like get the number of combinations with the friends included. So like to choose 5, I think, and then subtract
Say
that.
again? What's this? Say again?
And
What's
then
the
you could
second one?
you could subtract the number of like
Yeah, which is what?
to choose 8 or to choose 5.
Wait, what?
To
None of that
choose
makes
8.
sense.
Sorry.
There's no such thing as 2 choose 8.
Or sorry,
2
no,
choose
that's
8
not what I
is-
meant. Yeah, 8 choose 2 or 5 choose 2 is what I meant. Sorry.
Also, that's not math, right? There's no such thing as 8 choose 2 or 5 choose 2. That's not an expression, is it?
No, I just wasn't sure which one.
Well, okay. So your idea is good, but the execution obviously is lacking, right? So good. So what I'm saying, right? So here's the thing. Your approach is valid. You should carry it out to the end. How? Here is a number of ways for what? For
Number
the
of combinations.
friends,
Sorry. Yeah.
for 2 friends to attend together, right?
Yeah.
Agree? So I won't tell you what the answer is. I'll let you work it out for yourself because it seems like you're working on that. Once you do that, what should you do? Once you have this answer, then what you should do, which is the thing I told you to not do in general, is to check the numerical answer. Why? Because now you want to compare the numerical answer you get here with this answer and make sure that they are the same answer. Only then will you know that whatever you put here is correct. Is that okay? So I'll let you figure that out. But so your approach is valid. It's not that hard to write this down, but I'll leave it to you. Okay. All right. Any other question? Okay. So question B is what? How many choices if? Oh, actually, question B is that how many choices if 2 friends will only attend together? Sorry. 2. Okay, so actually A, they're feuding, but B, somehow they must come together. So they're different scenarios, but yeah, sort of this is exactly that one. So I will tell you anyway, right? Because that's the thing. But anyway, right? Can anyone tell me what the answer here is?
Six choose 5 plus 6 choose 3.
That's correct, right? So 6 choose 5 plus 6 choose 3. I guess, well, explain your reason.
So the first one is both of these friends don't go. So we choose out of the remaining 6, we choose 5 to go.
So both not invited, right?
Yes.
And then 6 choose 3 is?
if both of those are invited and attend.
Both, exactly, both invite. Right, so exactly, they only attend together. So, okay, so here's the thing, right? I guess there is a subtle difference between these two ways. So you want to be careful here. Here, I think you only subtract out, right, the cases when they both attend together, because that's a no-no. But right, if they both not attend, that's fine, right? You see the subtlety here, right? But in question B is talking about the number of ways to invite them. So of course, the possibility is you don't invite them. So I think, right, so what I'm trying to say is this question mark here and this may not be the same, right? I think this question mark here only refers to this. Is that okay? But again, right, please check, whether or not if you do this, then it agrees with that. I'm not guaranteeing it right now. Right now, I'm only guaranteeing that this is the right answer. This is the right answer. I'm also guaranteeing that this is a valid approach, provided you put in the right number here, okay? But yeah, the answer here must have also the 6 choose 5 component, because we must allow for the possibility that we do not invite both of them together. All right, any question? Very good. So let's do the next one, which is number 33. So we have 10 countries with 4 groups, right? So they are Russia, sorry, 10 countries, 10 groups, 10 people actually, including Russia, France, England, and US, to be seated in a row. Well, this is the question, right? But pay attention, because this is not a question assigned in this week's homework. I don't know if it show up in the future, but sometimes there'll be a question of sitting people in a circle, right? And sitting people in a circle or sitting people in a row, which is like, I mean, just a row, will be different. Yes. So you want to pay attention to this context. But here they sit in a row. And how many ways? So that, right, what do we have? French and English are seated together. Or next to each other, sorry. Wow. US and Russia are not. So again, right, the first thing when you do any of this question, if the scenario is not perfectly clear, is to run some example in your mind or on a paper on what should it look like, what are we counting. So again, right, I think the language is pretty clear. What we really want is we have English here, right, and French there, wherever they are, right, in the 10 seats. But US should be somewhere, and then Russia should be somewhere else, right? We should not have US and Russia next to each other. That's what they have. And then whatever other countries, right, to fill in the rest. And then how many ways can we do so? Well, this question is rather, I don't want to say hard, but it's an interesting question to demonstrate that you want to approach the question in the right way. Then it's easier. If you approach it in, let's say, not the right way, then it's harder.
9 factorial times 2 minus 8 factorial times 2 squared.
That's excellent. That's exactly correct. Well, I'm not so sure how you come up with this, but let's try to see if you explain this, and if the ones who don't come with this answer don't see the answer right away, don't feel bad. Yeah, but anyway, how do you come up with this answer?
So 9 factorial times 2. So the French and England, the France and England will be as one because they sit each other with each other like next to each other. So there will
That's
be
correct.
9 countries because yeah, and then times 2 cause France and England they can like switch.
Correct. Yep.
Yeah. Then 8 factorial is like we also see Russia and US as one.
Correct. That's
They
correct.
sit they sit
Mhm,
next to each
mhm,
other.
mhm, mhm. And then the 2 square is,
They both can switch.
that's correct. Yep, that's excellent. Yeah. So that's it, right? The way that this works, there are 2 things that you should pay attention to. The first is that, together here next to each other, wherever, can be viewed as a single unit, right? In which, right, they just move together, so we just permute them together. So that's why it's 9 factorial and 8 factorial, whatever, right? But of course, don't forget that within themselves, they can permute. So that's the 2. All right. So that's the first principle, right? Things that are attached to each other can be viewed as one unit, one object. The second one, right, is what I think has been mentioned before, but not really needed in that problem, at least, is to count negatively, right? So that's just my term, but you can count positively or you count negatively, right? What I mean, and I think it might make sense to you, is count positively. You just count the cases that work. For example, right? Both friends not invited, choose one, whatever, and then add them up, right? Both friends not invited, both invited, and add them up. To count negatively is you subtract away the undesirable cases from the total number of cases, right? So who knows? There's no rule that says one is easier than the other, right? It depends on the problem you're dealing with. Sometimes counting positively is easier. Sometimes counting negatively is easier, right? Here, I think both are easy, actually, right? It's just that, here we don't bother to work it out because I want you to think about it. But here, in this problem, I would say that counting positively is really a pain. The reason, right, is that if you want to count cases when French and English are sitting next to each other, but then US and Russia are not, basically you will notice, I encourage you to think of counting positively here to appreciate the answer here, is that it depends on where the English and French people are. It affects how you sit the US and Russia. And then the case becomes really, it's not that painful, but you have to do it case by case by case by case, and it's really long. On the other hand, to count negatively, you see that the principle of sitting English and French together and the principle of sitting US and Russia together are exactly the same. You just group them together and then you permute within. And that's why, right, I would say it's really clever. to think that, well, we want to keep them apart, right? But let's try to keep them together and then subtract away, which is, right, again, this sphere, right? So that's it. That's exactly what I want to kind of say here, right? That both are valid ways of counting. It's not a principle listed in the textbook, but it's a technique, right? That you want to keep in your mind when you do counting. And again, this is why these problems are interesting, because there's so many ways to do them that, you know, you have to be attuned to the problem to figure it out. All right, so with this, I'm gonna close the chapter, right, on combinatorics and move on to chapter 2. Any final question before we continue to chapter 2? All right, so now chapter 2, right? As we tried to talk about last time, is called axioms of probability. All right, and so I mentioned last time, right, that probability is basically a way to assign, right, likelihood to events. Let's say consistently or logically, whatever, right? So there are two keywords here, right? Likelihood, which is, you know, I think intuitively we know that it's basically a number between 0 and 1, right? All right, well, so we'll speak of that later. Events is denoted by a letter E or letter F or A or B, whatever, right? And so basically you can think of it like this, right? You have events which sit in a sample space. Sample space, you can think of it as like collection of all outcomes, if you will. So, sorry. I wonder, sample space is a set of all outcomes, yeah. So, and then, right, so basically it's E. And then you have an operator, is called P, right? It's P of E, right? And which maps this to 0 to 1, right? So you apply probability to the event, which spit out a number, right, between 0 and 1, okay? But of course, so events are like the domain of the operator probability, right? So there are rules to apply this operator to the events, but of course there are also rules for the events itself. You should be able to combine events in certain ways that still remain events, okay? So there are rules for the domain, there's rules for the operator, things like that. And that's what chapter 2 is about, okay? So 2.2, is exactly about sample space and events. So it's sort of like a little bit, well, not super rigorous, but it's rigorous enough. So first of all, right, you should pay attention to the keyword. I guess it's really outcomes and events. You don't have to really pay attention to sample space as much. But so basically, when you do an experiment, you will have outcomes, right? So for example, right, let's take the example of toss a coin twice, okay? Then it should be obvious that the outcomes are head, 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 tail, tail, head, tail, tail, right? And so these are all possible outcomes, agree? So meaning there's no other outcomes beside this. And we denote that by S, or, you know, for some reason, I like to use the word omega, it's up to you, right? S is the word that the textbook use. Omega is just the word I picked up, I don't know, a long time ago. And some textbook uses that. Basically, the collection of all outcomes, right, is the sample space, okay? Sample space is the collection of all outcomes. So, but is outcome the only, so of course, outcome is an event, okay? So you can put a probability on the outcome. And how do we do that? Well, if we think of all the outcomes as equally likely, then the probability of an outcome is just 1 over, right, the number of outcomes. That's where combinatorics comes in, right, to tell us how many outcomes there are, for example. But what I'm trying to tell you is that outcome is not the only event possible, okay? So basically, you can think of outcome as the smallest event, meaning that there's no sub-event inside, okay? But what can be a bigger event, and big or small here is in terms of set, right? A bigger event, for example, will be this event, right? Head-head union with head-tail. All right. What is this? This is an event that tells us that the first toss is head. All right. Well, so first of all, notice that, again, this is a little bit pedantic, right? Stay with me, but that's how we describe things. Basically, we're trying to say that we can union events and we still have event. That's the rule, okay? So basically, right, this or that is still an event. And again, right, why do we care about this, even though it's pedantic? It's the reason is we want to say that the probability of this is still a legal thing to say. But yeah, of course, right? But there you go, right? That's the rule. What else? Well, complement of an event is an event. For example, what is this? Well, clearly this is, right, the remaining 3. Right, because not this is the remaining 3. Well, there's nothing, you know, well, it just say that, right? At least 1 toss is tail, right? Things like that. Of course, notice that I have quickly switched from English, right? Sorry, from the descriptive language of the outcomes to the English language, which is right, fine. You see that we can be flexible and nimble. And what I'm trying to tell you though, right, is that it should be no surprise that a complement of an event is an event, but that's the rule of events. All right, so basically, again, what I'm trying to say is that outcome, this is for discrete probability anyway. Outcome is the smallest event. When you union event, you can get bigger event. So you union up outcomes, you get event. Or right, event, union event is an event, right? Complement of event is an event. From which I won't tell you how, but the combination of, well, maybe I'll tell you. Combination of union and complement will give you intersection. So it will also give you the idea that intersection of events is an event. All right. So basically, it says that events are pretty robust under the set operation, right? Another way to say it is events are closed under union, intersection, and complement. But at this level, I won't bother to tell you all the details, but it is not really always true. There's a keyword called countable. Countable union events event, countable intersection events event. You can mess things around when you have uncountable, but you know, unless you take real analysis, these things that I'm saying won't really mean much, and we don't really need to go there. But what I'm saying is, like, yes, things are pretty intuitive here, but there's there's some reason why we okay, list this up. All right. So what else? So these are rules of events, right? Notice that. So for example, what is an example where we say intersection events an event? Well, for example, right? First toss head intersect with second toss tail is of course the outcome of the event head tail, right? Like, okay. Now again, right? Events or outcomes are objects that are legal to talk about the probability of. In other words, right? Events is the domain of probability operator. We can only apply probability to an event, and so okay. The next thing I want to talk about is some basic properties, right? And these are really just set language. So the union is commutative. The intersection is commutative. All right. So by the way, right, the notation EF right here is E intersect F. So this is commutativity. All right. And by the way, right, what do we mean by EF, things like that? So you can just pick whatever and you call E. For example, right, first toss is head, you can call this E. Second toss is tail, you can call it F. Right. And again, it's not anything. If you intersect these two, doesn't matter which order, right? You intersect them in, you will still end up getting the head tail outcome, right? Notice, of course, when we put F over here, because F is already saying second toss is tail, right? The order of F intersect E doesn't matter, okay? Don't confuse it to say, okay, somehow F intersect E is going to be tail head. That's not true. In our language here, F is second toss tail, so it doesn't matter. The second thing is associativity. Which says E union F union G is E union F union G. E F intersect G is E intersect F G. Distributivity says E union F intersect G is EG union FG. E intersect F union with G is EG union FG. Sorry. I think, hold on. How do I? So this is clear, right? This is E union F intersect G. The textbook says this is E union G intersect with F union G. So I believe that the way they read this should be like that. They don't have a parenthesis here, but I think it reads like that. I'm not so sure if you have EF union G like this, it will read the same way. So yeah, the textbook doesn't put parentheses on, but I think here it should be like this. Okay. All right. So anyway, right, these are all set theory thing, basic set theory stuff, right? So the reason we care to know this is because, for example, once in a while you might have probability, right, of E union F intersect G, like that, right? You want to calculate that probability. Now, it might be hard to operate with this because you will learn that probability of an intersection of two sets is not something that's very easy to work with. But if you use distributivity, and you know that this is EG union with FG, and then you can use the union law of the probability to work it out to be something. All right. So that's why we kind of write this down, not for pedantic purposes, well, maybe, but also, right, because it might have practical application when we have to operate these sets in a certain way so that it's easy for us to apply certain law to it. All right. Last but not least, maybe, is De Morgan's law. Which says that the union of the, let's say, the complement of the union is the intersection of the complement, right? Like that. All right. So I will pause here to see if there's any question. I suspect there's not much to ask, but so like, okay, so let me recap. Basically, 2.2 is just careful to tell you that, right, or at least lay out to you what the language of a sample space means, outcome, events. Right now, I don't see there's much for you to use this on because a lot of times it's clear. This language might be a little bit necessary or useful when you move on to modeling, which is 478, because then you have to actively ask yourself which sample space you're operating in, what are the events, etc. Okay, because you have to come up with the sample space yourself. At the level of this class, I would say that most of the time the sample space is very clear. There's no choice. You just work on, let's say, the toss of two coins. There's no choice. So it's not that hard. But again, right, then the message is that it tells you certain ways to combine events and how the events interact. Because in the end, right, we'll apply probability on events. So if we don't understand how events interact, right, using the set language, for example, this, then we might have a hard time manipulating, okay, certain kind of probability expression. For example, right, let me just give you an example. I mean, it probably should be clear that probability of E complement, right, is 1 minus P of E, right? This is exactly the principle of negative counting. Whether you count positively or you count negatively, right, and then subtract away, is something that you will also have to deal with in probability. But what I'm trying to demonstrate is that, right, for example, and it's a problem I just did with my 478 class, which we might also do in this class, is that if you somehow, let's say, do the complement like this, right, of two sets, right, you want to find the probability of intersection of the complement of two sets. Now, intersection, again, is something that's not very easy to manipulate. But if you realize that this is 1 minus a probability of the so first of all, by De Morgan's law, you recognize that this is the union of E and F and then complement, right? Like that. And then you will see that it's going to be 1 minus a union. And so this operation, right, lends you on focusing on the probability of E or F instead of the probability of E, not E and not F. And again, that kind of small switch somehow makes things much easier to calculate. And that's exactly, you know, what these rules are trying to tell you about, right? Again, it has the example in the previous chapter that we deal with, right, is the principle of, you know, count positively or count negatively. That's exactly what's going on here as well, but under the set language. All right, any question here? Okay, so moving on to 2.3. and this is called the axioms of probability. So, right, we just talked about how events should behave. Now we'll talk about how to assign, right, the likelihood to probability. So any probability, right, of an event should satisfy three things. The first thing is that it should be a number between 0 and 1. Well, right, that's kind of somehow the convention. Oh, by the way, right, not sure what happened in this class because I will actively discourage you from writing down a numerical answer. But just if for whatever reason you calculate out something like this, you should just ignore your effort and go back to square one and recalculate, okay? Because, well, trust me, I have seen this more than once. I don't know why, right? The student would believe that something like this can earn any credit because there's no probability that's negative and there's no probability that's more than one, right? So anything like this, just don't even entertain that thought, right? But like I said, right, this is also a reason why we care for expression rather than numerical answer, because expression can be corrected, right? Expression carries meaning and you know what you're trying to write down with certain kind of expression. Two, the probability of the sample space, right? Or probability of, so here, right, I'm just writing down two ways to say the same thing. Or like I said, right, this is a universe, right? This is everything. The probability of everything happening must be one, it's guaranteed, right? That something has to happen. And the third, so these two are pretty trivial, but you know, who knows? The third one is the one that really matters. It says that if you have a collection of mutually exclusive events, and what do we mean by mutually exclusive? What it means is that all these events have nothing in common, right? This is the notation for the empty set, right? So you take any set, they have nothing in common, all right? Then the union of these guys, you take the probability of it, is the sum of the individual probability. Now, the notation here goes up to infinity. Most of the time we will do finite union anyway. So I think, right, in particular, you can have something like this. This is probably the most basic version that you want to pay attention to. There you go. That's it, right? If two events have no intersection, then the size of the union is a sum of their size, right? And by the way, right, having said that, a lot of times to gain intuition on probability, right, the Venn diagram is useful, or it's very useful, right, at least at the basic level, to give intuition. So here, right, this can represent events. Probability can be imagined or visualized as the size of the circle, right, of the how big or how small they are. So, right, the size of the union of two circles, if they have nothing in common, is the sum of the sizes, right? Which is obviously true. Notice, right, something that's not true is if they have something in common, then the size of the union is not the size of the individual pieces add together, because then you will double count, right, the intersection, which is exactly the inclusion-exclusion principle formula, right, that we'll be talking about. So what I'm saying is, like, you know, by drawing the Venn diagram, you can check, right, to see if certain kind of intuition is true. Right now, right, 1, 2, and 3 are very, very basic and simple, nothing surprising. It's pedantic even, but we need to write it down just to, you know, get over with. All right, any question? All right, so, well, since we're being pedantic anyway, right, let's just now write down a simple consequence, right, which we already assumed, but we already talked about. So if we have a sample space of n outcomes that's equally likely, then probability of one outcome is 1 over n, right? For example, right, is the one that we say toss a coin twice, right? Head, 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 tail, tail, head, tail, tail, right? Then probability is 1/4. Now, where does this come from is the only thing I want to say, right? So where this comes from is from the axiom of probability, right? It's actually 2 and 3. How? The reason is this, right? If we look at P of head, sorry, P of this omega, right? Which is 1. This is axiom number 2, right? On the other hand, omega clearly is the union of this, right? And these guys are mutually exclusive, right? Because you cannot toss the coin twice and get both head, head, and head, tail, right? They're mutually exclusive. So by axiom number 3, right? And now using the assumption that they're equally likely, that's the assumption. That's going to be 4 times, say, P head, head. So this is the equally likely assumption. Right? And then, of course, you divide by 4, you get that to be 1/4. All right. Again, a piece of pedantic argument, right? And whatever. But the message here, though, right, is that this number, as I explained, which everyone takes for granted, like, oh yeah, of course, it's 1/4, does not comes from 1/2 times 1/2, as a lot of people assume, right? The 1/2 times 1/2 makes an extra assumption that the first toss and the second toss are independent, which is nowhere encoded in this setup. All right. In fact, independence down the road, as you'll see, is a consequence of equally likely assignment or equally likely assumption. So people get things in the opposite way, which is wrong anyway, right? Because they make an extra assumption without having the reason for it. But what I'm trying to say, right, is all these things come from a setup, comes from a model, comes from assumption. Again, you don't have to be aware of all these things to do probability, but you should know that they're rules and they come from they come from somewhere. And then if you make an assumption that is not within the rule, you should know that you're wrong because the assumption is not there. Okay, that's all I want to say. All right, so having said that, let us move next to 2.4. Oh, maybe let me pause, right? Any question about any of this? All right, so some simple proposition. So basically, right, coming from these axioms, there'll be some small consequences like this, right? But, you know, continuing on along that theme. So the first is that the complement, right, is 1 minus that. Again, note that I don't think this is surprising to anyone. I even used this, right? I even wrote this down before. But this is, notice, this is something that is to be proven using the axioms, right? So, well, how to prove this? P of E complement union E, right, is P of omega, which is 1. But then, right, on the other hand, this is also equal to the sum because they are mutually exclusive. Like that, right? So anyway, let's not make a big deal out of it. But again, right, it comes from axiom 2 and 3. Second one, if E is contained in F, then PE is less than equal to PF. All right. So the second one says that if you have a sub-event, then the sub-event is always no more likely, right, than the original event. All right. And notice, right, in the language of logic, E contains in F is the same as say E implies F. All right. I won't harp on this, but you can check that, right, in a lot. Basically, it says, right, if you're in E, then you're automatically in F. That's why it's E implies F. So down the road, maybe that if you read out something that says an event implies another event, right? For example, let me show you, right? For example, if you have the first toss is tail, sorry, if you have the 2 tosses tail, then clearly it implies the first toss is tail, right? I mean, that's clear. Or if you want, the outcome tail is a subset of tail and tail head. Says the same thing. But of course, right, in terms of probability, then the probability of getting 2 tails must be no more than getting the first toss's tail. Is that okay? Something like that. Again, right, that's obvious. But, right, so what's the proof of this? Well, the proof of this, right, is because, you know, if E is contained in F, then F is E union with something we call F but not E, right? So F is not E, it is F intersect with E complement, right? In terms of the Venn diagram, then is F is E, right? This is the part where you say F but not E, right? So anyway, right, the point is that notice that by the, and this is a piece of pedantic argument, but you should have it there. E complement is an event because E is an event. F intersect with E complement is still an event because events are closed under intersection. In other words, I'm just saying that this is an event, right? Therefore, it's legal for me to apply probability on it. In other words, right, E and F but not E are 2 mutually exclusive events. Okay, and that's why I can apply the rules to it. All right. So it's legal for me to write this down because F but not E is an event. Now we will use axiom number 1 to say that this guy is non-negative. And that's it, right? This will show us that PE is less than equal to PF. Okay. So to recap, right? The first one is about complementary. The second one is just about containment, a comparison kind of principle. The third one is the so-called inclusion-exclusion formula. Oh, sorry, EF. Right, so this is called the inclusion exclusion formula. All right. So how do we prove something like this? Well, we prove something like this by, you know, the Venn diagram, for example, right? And so you have EF here, right? So you can do something like this. Notice, right, the key to arguing any of these out, I mean, there are many ways to do it, is the taste, right, is that we're trying to follow the axioms, especially the third axiom, which allow us to add probabilities when we look at the union, as long as the events are mutually exclusive. So, right, the problem, of course, is E and F here are not mutually exclusive. So it doesn't matter, right? We can do something like this. We can split into E, but not F, which is this part. EF, which is this part. And then F, but not E, which is this part. All right. And of course, I guess I skip a step here, right? Where I say that E union F is really the union of these three guys. And these three guys are mutually exclusive. That's why I can split them up. But that's the reason, right? So that's E union F. And now how do I reconstruct the right-hand side? Well, easy, right? Because basically it's clear that this plus this is PE, right? So you know what? Maybe let me just be even more pedantic, right? And then do the union so it's clear for you. So first of all, E union F is E but not F, union with EF, union with F but not E, right? In which case we can split. And now we're going to be pedantic again, and now we will union this up. And then we'll union another piece up. In which case, right, we use EF again here and here, but we only have one EF, so we have to subtract. Does that make sense? Right, so we move this inside with the union because they're mutually exclusive anyway. We'll move this inside because they're mutually exclusive anyway, but we have to subtract one away because we use it twice. But then, right, this is exactly PE. This is PF minus PEF. Is that okay? Any question? All right. So maybe, right, I've been doing a lot of pedantic things. So let's throw a quiz at you to see if you follow this. Oh, sorry, what quiz is this? Quiz 6, I think.
Quiz 5.
Oh, thank you, appreciate it. All All right, so Jay is taking 2 books, right, for vacation. She likes the first book with probability 0.5. The second with probability 0.4, and likes both with probability 0.3. Okay. What's the probability she will like neither book? All right, does anyone have an answer for this? So with a question like this, right, it's always good to go with notation. Notation is how you control, right, a word problem, which is, I think, a favorite of Ross. Or, in general, right, it's good to do word problem. So you would want to denote, let's say E is the event that what she likes, the first book. F is the event that she likes, the second book. Right? And then write down the information that is given in terms of the notation. For example, what do we know? We know that P of E is 0.5. P of F is 0.4, right? The event that she likes both book would obviously be P of E. 0.3. All right. Now, what is the question in terms of notation?
Is it 1 minus P of E union F?
Yeah, so let's just, you're correct, right? But let's just, for now, the question is asking for P of E complement, F complement, correct? Right, it's asking for she will like neither book. And exactly, right? Now we see that we've switched this to E union F complement using the Morgan's law and using complement rule. All right, there you go. And how do we do P E union F? By the inclusion exclusion formula, right? Which is 0.5 plus 0.4 minus 0.3, which is 0.6. So therefore, the answer is 0.4. There you go. Okay, any question? Okay. So now, let's conclude this, right, with the so-called general inclusion exclusion formula. And by general here, I mean with more than 2 events, right? This is 2 events. So let's just take it slow. What do you think if I want to union 3 events up? How will I do it? If I add this up like that, is it correct? In general. Well, the answer is obviously no, right? Because you see, if this is E, F, and G, these are E, F, and G, then when you add them up, you will clearly overcount and also triple count, right? So no. So we need to compensate. How do we compensate? Well, you need to subtract the parts where you double count. All right. So, right, you double count this region, you double count this region, you double count this region, right? So you subtract like that, you will no longer double count. However, right, you triple count this region, right? But if you double count, you subtract each of this, then you subtract each of this region once, in which case you triple count when you subtract it twice, meaning you don't have it, right? So right now this expression does not include this region, so you add it back up. And so that's the inclusion-exclusion formula at the 3 set level, right? Level. Any question? Well, then what about inclusion-exclusion formula at the general level, meaning N level? What should that be? Well, as you may guess, it's going to be the sum at the first level. Just sum them up individually. Then you subtract them pairwise. And of course, right, you see now, it's kind of very tiresome to list out all pairs. So you do this notation, and you do I less than J. Okay, let me explain. So this really is about 0 less equal to, sorry, 1 here. I start at 1 up to N. So this means, right, you pick any pair ij between 1 and N, for example, 1 and 2, 2 and 4, etc. However, right, there's a restriction of I less than J. So you're not doing 2 and 4 and 4, 2. Okay, you only do it once. Why? Because notice right here, the pairs, you only subtract the pair once. You only do EF and then you do FE. Because you have a 2 on it. So that's why in this notation, I less than J, to prevent us from subtracting things twice. We only subtract it once. We subtract every pair once. Are we okay with this? Similarly, right? But now at the triple level, then you have to include all triples. But it's going to be at, and then it's 1 less than equal to I less than J less than K, like that. Okay. And then you add, subtract. So basically the pattern, right, is add, subtract, whatever, right? But anyway, right, at the end, you will do the intersection of all events. But what is the sign for the last object, for the last term? What would it be?
Would that depend on the number of n, whether it's odd or even?
Correct? So how do we express that?
Negative 1 to the power of hold on. Yeah, negative 1 to the power of n minus 1.
Good.
I think.
Or I think is correct, but I think draws to also n plus 1. You're right? Yeah. So for example, at the first layer, right? First, it's 1 plus 1, so it's even, so no, is add. At the second layer, right, is 2 plus 1, so it's odd. So yeah, it's n plus 1. That's correct. All right. Any question here? All right. So let's do an example, and then we're gonna call it a day. So this is a quiz even, right? So it's quiz 6. So this is the so-called hat problem, which is very well known. The scenario is like this, right? Let's say there are n gentlemen. Right now, let's just say 3, right? 3 men throw their hats together. And then, right, select them randomly, right? Select a hat randomly. Okay. And suppose that all things being equally likely, okay? Let's say that each hat is equally likely, right? To be selected by any method. Right? What are we after? We're after the probability of no man guess their right hat. Okay, that's a question. But just to warm up, maybe let's start with this question. What's the probability that all men get their right hat? What is this? What is the probability that all men get their right hat?
1/3 factorial.
That's correct, right? 1/3 factorial. And the reason, right, is simple. So here's 1, 2, and 3, right? There are 3 factorial ways to permute the assignment, right? For example, if we write like something like this, that means, right, the first gentleman gets a third hat, third gentleman gets the first hat, the second gentleman gets the right hat, right? For example, things like that. So there are 3 factorial ways to assign, right, the hats to a gentleman, out of which, right, there's only one way to have everyone having the correct hat, which is 1, 2, and 3. All right, you see combinatorics at work here, right? That's exactly combinatorics for you, right? 1/3 factorial. Any questions so far? All right, so how do we deal with this question? Probably no man gets their right hat.
Wouldn't it just be 1 minus 1/3 factorial?
Incorrect. Because, yeah, when you do this, right, let's see, logically, what is this expression? It's probability of what? Well, what you're thinking of course, is probability of all men correct complement, right? Agree? That's what it is. But what's the complement of all men correct in terms of logic?
Somebody gets one incorrect.
Yeah, at least one man get the hat incorrectly, right? At least one man hat incorrectly. But does that mean all men gets the wrong hat? No, right? This is equal to probability that at least one man gets the wrong hat. But that's not the same as the probability of all men gets the wrong hat. Do you understand? So it's not 1 minus 1 over 3 factorial. Right? For example, this is counted under this because 1 gets wrong and 3 gets wrong, but it's not counted under this because 2 still gets it right. Are we okay?
Yeah, I see that.
Yeah. No, it's fine, right? It's a common logic mistake. At least one, and then all. All right, so let me write down something quickly, and if we are not finished today, we'll continue next time, okay? Once again, actually, this is not an easy question. It's not something you can just write down right away. The way you proceed is, again, through just procedurally write down the events you want. So you let E1, right, be the event that the first man gets his right hat. E2, second man, so on and so forth, right? Then what are we after? We're after a probability that no man gets their right hat, which means what are we after? We're after probability of E1 complement, E2 complement, E3 complement. Sounds familiar? Which is kind of similar to the one we just did above, right? But now with 3 events. And so how do we deal with this? Well, I guess intuitively, right, you want to use the Morgan's law to turn this into a union. And then do 1 minus, right? And then how do you deal with the union? You would use the inclusion-exclusion formula, but at the 3, right, the general one, to calculate it. See? All right, so I think we're out of time, so we're going to stop here, and then we'll pick it up right here next time. But what I'm trying to tell you here, right, is that for this problem, the hat problem, is a perfect illustration of the inclusion-exclusion principle at work. Without using the inclusion-exclusion principle, you will not get this answer correctly. All right, so okay, so I'll see you on Friday. I'll post some homework problem for this lecture today. If there's any question, I'll answer them. If not, have a good day, and I'll see you on Friday.
Thank you, Professor.
Thank you.
Thanks.
Thank
Yeah.
you.
Hello, Professor?
Yeah.
Just wondering, did you see the email this time? If not, I might have something going on my side.
1 second here. Alexander, right?
Yeah.
Let me check real quick. When did you send it?
Right after class, on Monday. No? Okay, maybe
No.
maybe I'm doing something wrong.
Are you from Rutgers?
Yeah.
That's
Maybe
weird.
I'm sending it to the wrong place. I don't know. I think there's two different email. Maybe I'm sending it to the wrong place.
There are
I'll,
two Professor Phams in the math department. Our names are very similar, but I'm not sure if that's
oh no.
it.
I don't know. Okay.
Yeah, that could be, but I did not see your email at all.
Maybe. Okay, maybe that's
By
the
the way,
case.
yeah, check. Yeah, you don't want to send the email to the
That
other
would
professor,
be
but
very unfortunate. So, all right. Sorry for bothering you with this. It's been a pain.
sure. But the point is, I asked the course coordinator, but I don't think the coordinator responded to me yet. So
Okay.
there's no response. Okay,
Okay.
I'll have to wait response. Okay.
Okay.
Yeah.
Thank you. Have a good
Sure.
day.
You too.
Hi, Professor.
Yeah.
I also have same question because I also sent you an email after the Monday's class, but I didn't have the response yet.
Let me see here. No, I don't receive any email from you either. What was your question?
Oh, for Philosopher's quiz, because I don't know the quiz should submit by this week, so I